Hello all. My name is Neil MacDonald, and I'm here to talk to you about hacking compiled code with a slant on replacing functionality with Rust. You may already be an expert at this. You may already know what I'm going to talk about here. In fact, as Kira mentioned earlier, testing the limits of our knowledge could easily get stuff wrong on my end, so please let me know if I do, first of all. So in terms of injecting Rust code into already compiled code you don't have source code for, I did this for my own project called Norn Pulse, which I'll be using as an example of how to do it for yourself in this project here. So as you can imagine, this talk will focus on low-level binary details, I'm afraid to say, and in particular, we're going to be looking at a lot of unsafe Rust, possibly making Rust more unsafe than you perhaps ever thought possible. I post the Sardinia nuclear warning message here just to hammer home the fact that while this is fun to do, it's not exactly a good idea in general, but it's definitely entertaining. So primarily this talks about having fun, well, breaking things. You don't need to do this in Rust, but there is a strong focus on Rust in this talk, obviously, and there's a lot of cool features in Rust that help me achieve my aims in fulfilling this project. So in terms of outcomes, my primary hope is that you're A, entertained, and B, you come away having learned something new about what's going on under the hood. In terms of structure, I'd like first to go over a quick overview of my Norn Pulse project, why I was motivated to do this. Then I'll go into the executable file format, do a whistle-stop tour of what a PE file is, and looking to how to inject Rust DLL as a dependency into that. I'll be going into reverse decompilation tools to make sense of function boundaries, and then how you can edit those to call Rust code. We'll then be looking to calling C++ code from Rust, and finally a technique called hot patching, whereas you can replace C++ functions with Rust functions at the end. And I'll probably conclude with what I've actually managed to do so far in my own project, and just kind of conclude there. So do feel free to ask questions throughout. You can shout them out, raise your hand, type them in the text box. If I'm unable to answer your question in the moment, we'll come back to it at the end of the talk. I promise not to go over the 45-minute mark. Hopefully it'll be about 40 to 45 minutes, so there'll be plenty of time to go over questions at the end and any other business. That's the plan. So first, Norn Pulse. So talk about the game that I'm actually attempting to modify here. So the year is 1999, and a game called Creatures 3 came out, and 2001 a game called Docking Station. That's maybe a bit loud. Can you hear the music on that, by the way, out of interest? You can't? No. Well, let me just turn it off for myself then, at least. So this is a simulation game where represents probably the most advanced simulation game that ever came to market at the time it came out, and argue over 20 years later, possibly still the case. So in the simulation game, you have these creatures on this spaceship-esque terrarium ship through it there, and you can raise them, get them to survive, that kind of thing. And the creatures here are called Norns, hence the name of the project, Norn Pulse. So the problem with this game is that it's becoming more and more difficult to run it on modern systems as time goes on. It came with a suite of tools originally, which no longer work in terms of like inter-process communication. Something fundamental has changed in the OS 20 years on, obviously. And I wanted to try and preserve this game for myself and for future people as well, because I think it's worth preserving. In terms of some of the cool features, it has, the creatures have genetics. So I can load up a genome file, and you can see the creatures have genes there. These genes define organs, which perform functions. For example, digestive organ takes glucose and takes starch to produce glucose. The creatures interact with their world entirely through a system of chemicals. So, you see the chemicals there. about 161 in total. So for example, if a creature's standing around, then its lungs produce the oxygen chemical. If it's in water, lungs will produce the carbon dioxide chemical. The Norn will be drowning. And there's a limited AI section to this as well. We can load up. The genetics also defined the creature's brains, showing off what adult brain here looks like here. So you see the different lobes of the brains, one controlling speech, such as noun and verb, the attention lobe of what it's looking at, and so on and so forth. If you're interested in actually the more kind of nitty-gritty details, there's a creator of the game, Steve Grant, who made a book called Creation, Life and How to Make It. It's a really interesting read into kind of the concept of trying to write simulations and AI and the limitations of 1999 hardware at the time. But for our purposes, we don't really care what the game is. I'm just trying to sell it to you at this point. What we really care is how it's made. What I can say, at least, well, it's an x86 assembly. It ran with C++ source code, and it was built against the Microsoft Visual Studio 6.0 runtime, which was released in 1998. That's right, Visual Studio existed in 1998. I didn't know myself. So in terms of what the structure of the executable file looks like, though, is it follows the PE file structure. And I'm sure many of you are probably already familiar with PE files, but I'll go over them anyway, just in case. So when we compile native code to Windows, we are placing our output in something called the PE file format. It doesn't matter if it's an object file, a DLL, or an executable, it'll eventually end up following this structure. And it has remained relatively the same for the past 20 years. In fact, it doesn't matter if it's an executable built in Visual C++ 1998 or Rust compiler in 2023, it's going to be like this pretty much. In terms of a tour of just the structure, PE file always starts with a DOS header and a small DOS program. You can modify this to whatever you want in the linker, but the default DOS program normally prints something along the lines of, this program cannot be run in DOS mode, and then it exits. What follows are headers that define file sizes, section alignments, the starting point of code execution. But what we're really interested in for our purposes are the sections. And understanding what a section is, I'll open up a little cool tool here called PE Bear, supposedly used by the CIA too, I'm told by the creator of it. And you can see in here that it shows all the different sections of the PE file in here, gives some relative sizings. So what we understand is that when you load up an executable or pull in a DLL as a dependency, the OS will use a loader to load up the PE file, and it'll start copying the sections into memory. And each section is earmarked with its memory access rights. So .text section, that contains your actual executable code, is marked as executable memory. Your RData section is your read-only global memory. So in Rust, if you had like a string literal, it would go into this section. The .data section is marked read-write memory, and this would be for things like static mut in Rust as well. So that would, all your static mutable global data would end up there. The section that we're really keen on for first injecting Rust into this binary is the iData section. And this is a very important one because it contains information on our exports and our imports from the executable. So the export section, you can see here, it's got quite a lot of C++ mangled function names. If this was an actual DLL, this would be a lot more relevant because these would be the exports from the DLL that dependencies could import. The import section, however, is a list of all the libraries that are in the system and the functions that we need to access down here. So, for example, from the Microsoft Visual Studio 6.0, we've got all these. What makes the iData so important for our purposes is that this is the entry point for getting Rust as a dependency of the executable. So in terms of what happens in the actual PE file is that you have the import directory table, and within that there's an import lookup table ILT and the import address table IAT. So on that inside the ILT, this is just a list, a table of rows of all the function names. And on the right, and that's just copied into memory wholesale, it's unmodified. For the IAT, the import address table, when the loader copies that from the PE file into the memory of the running process, it replaces all the rows with the pointers to the functions that are to be called. So whenever you want to call an external library's function, you have to first look it up in the table and call the address in the table. So what we want to first get Rust into this binary executable is to add a new row to the import directory table, and that will trigger the loader to load up the Rust DLL into the same addressable memory space as the original process. And we can inject a method into the row of the IAT as well. In terms of actually doing this, you can use any tool. PE Bear is a pretty good one for it. If you load PE's engine.exe, it actually has a little wizard for adding records to your table, and it will do all the clever things like reallocating your iData and doing all the reallocations necessary. But you could do it in Rust, you could do it in PowerShell script, you can do it however you want. I actually used a program called IID King for this, which is why it's added an IID King section. But if we look at the imports, you can see that it added one I prepared earlier, is that I've added a Norn Pulse.dll as a library, and within that, there's a Norn Pulse main. So that's a line in the ILT, and when it's loaded in, an address will be provided by the IAT, provided the loader can find the DLL at runtime. Just that's how any normal loading DLL works. So that's a great start. The problem is that while the DLL might load up along their executable, it doesn't do anything. Nothing runs. So the next step is we need to actually get the executable to run something from the DLL itself. Well, how do we do that? So to find where we need to add our hook call, we could look at the .text section perhaps and look at the disassembly, but I don't understand x86 disassembly, maybe you do, but the compile C++ code is pretty difficult to parse at the best of times. But there are tools that do it for us. So, for example, Ghidra. You might or may not have heard of Ghidra. It was a tool that first came to light in 2017 as part of WikiLeaks, in fact, because it was exposed as an NSA tool. And as part of a public relations exercise in 2019, they open sourced it to try to improve their image, which was not very popular 2 years after WikiLeaks. What makes Ghidra a pretty interesting tool is that it converts assembly into C-ish code. So let's go to engine original.exe here. So if we open up, and this text isn't too small, I hope. Is it okay? You can kind of read. Okay, sure. So here, I'm in a function called entry. On the left-hand side is the original assembly. On the right-hand side is Ghidra attempting to convert it back to a CS code. And it's still pretty ugly, but we do see things now like function boundaries, and we see if statements and while loops, so it becomes a bit easier to manage. Now, interesting about the entry function in a PE file is that the entry function does not equate to main. Normally, if you're compiling for Windows, the entry section starts up, well, in this case, it'll start up the C++ runtime, and then it will call main. So you'll see all the way down here after doing a lot of gubbins, we get a call to W win main down at the bottom. Those of you who worked with Windows C++ before will probably recognize this as the classic Windows method signature for doing windowy things. So you can see within there, that is very much likely to be the actual start of the actual code that the original developers wrote. We see references to things like a logger called flight recorder, and a bit further down, we'll eventually start seeing bits and pieces like peak message A, wait message. So a message pump, which is the classic Windows ways of controlling the game loop and controlling the way that input output works as well by pushing all through this message pump at the center of the application. So what we'd really like to do to get Rust in here, like the first thing we'd like to do is to replace this call to when main to a call to our Norn Pulse main function. The question is, how do we achieve it, right? How can we achieve it safely? And this is where a bit of knowledge about calling conventions and what they mean at the assembly level comes in handy. So I'll try to go over that very quickly. So after all that, actually showing some Rust code for the first time. So some groundwork. We have an extern keyword in Rust. The keyword is actually quite context sensitive. It has multiple behaviors, but for two of them, the keyword is often used to declare our library's exports and imports, especially if your target type in your cargo.toml is c.do lib, executable, so on. So if you're compiling for a DLL in Windows, the first function is an import because it's a declaration and we see the little link statement. So this would be added to the import table of our PE file. The second function here is a definition. It's got a method body, and this would be added to the export table of our library. Now, obviously, we care more about the second form than the first for our purposes because we're trying to export functions from a library to be imported into an executable. But we'll want to start importing later on, but we won't be using this method here. But there is a second usage for the extern keyword, and that is it defines the calling conventions of our functions. And this is the important bit. And what I'm about to talk about right now is very x86 specific. So what I'm talking about, if you work in x64, I see the chat's kind of going, Peter data game. Oh, thank you all. Those questions, right? Yes. So the term to the extern keyword, where was I? Yeah. So what are calling conventions? That was it. What are calling conventions? So let me just pull up this Visual Studio code here. Drag this over. So at the assembly level, if we take a look at it, there is no such thing as a function necessarily. There are call opcodes, and then there's some stack manipulation that happens beforehand and some stack manipulation that happens after the fact. What a calling convention means is it is a way for the caller and the callee to be in agreement of how to set up and tear down a function call or how to pass information effectively. When you have a calling convention, it defines such ideas as what is the order of parameters are passed? Is it left to right to left? Which parameters go into registers? Which parameters are pushed onto the stack? For example, certain calling conventions like cinstd call push floating point numbers into certain registers and integers and pointers into EX registers and so on. It also defines what registers have to be reserved by the caller, reserved for the caller, that is, the callee isn't allowed to touch them. And things like what is responsible for preparing the stack and what is responsible for cleaning up the stack after the callee has finished. So, for example, we take a look at two differences here. So these four functions are all the same. They all have the same inputs and they all return the value 10. And then we have four functions at the bottom, which just call those different calling conventions. And if we look at the assembly here, I would call ccall and stdcall here specifically. The only difference between a ccall and a stdcall in x86 is that in a ccall, it is the caller's responsibility to clean up the stack after the callee is finished. A stdcall, it is the callee's responsibility to clean up the stack. And you can see that happen here in this very simple assembly, because in here, the ccall, it manipulates the stack pointer to allocate on the stack. At the very end, it deallocates the stack pointer after the callee is finished. The stdcall, you can see it allocating the stack, but it doesn't do any deallocation afterwards. But you do see it happen up here. So the difference in the ret assembly calls is that this one is blowing more of the stack when it's returning. So it becomes the callee is cleaning the stack through this method. And I know this is very detailed and there's no quiz on this, but what I'm trying to emphasize is effectively there are differences and there are consequences to these differences. So when we look back at Ghidra for these C-calling convention, we see that, well, Ghidra thinks that W1 main is a stdcall, say so here. And the reason it thinks it's a stdcall is because it sees stack being set up before the calling and the callee cleaning up the stack. It's not happening here. So it's making a reasonable guess. So bearing in mind that a calling convention is used, or at least according to Gitra, then all we really need to do is our Norn Pulse main function in Rust, as long as it follows the same set of parameters, has the same calling convention and has the same return type, then we can just replace this single line here and call the Rust code instead. And that's all we need to do for it to work. So how do we do that? So again, here is one I prepared earlier. Really, all you have to do is edit it in Ghidra. You can edit it in a hex editor, just right click, and you can even edit in a text editor, so probably not a good idea. But you just, in this case, what's changed is that this line here has changed from this call code to calling something within the binary to calling something that's a row in the IAT table. And Ghidra has actually been very helpful because it actually says, hey, I know you're trying to call Norn Pulse main here. It recognizes it because it's linked it up to the ILT. So then, okay, the engine has been modified. We've got a call into Norn Pulse main. And all that really remains to be seen is we just need to specially craft our Rust function to be called. So let me just find the right one. There we go. So this is our Norn Pulse section here. So you see we got our Rust function. It's started calling conventions, has the same arguments, and all it does is it prints hello world. And if we run it with any luck, what do you see here? Executing task engine.executable, hello world, and exit. A lot of work to get hello world into the system. But now we have control from the Rust end of the original compiled binary. We have complete control and we can start doing whatever we want. So next steps now, let's call C++ code from Rust. So let's try calling the original main function from Rust. So I want to maybe print hello world, start the game, print goodbye world, right? So how do we do this? Well, remember the kind of the extern keyword I mentioned, earlier for importing from C libraries. That's not going to work in this case, right? It's not going to work because there's no IAT for the loader to start putting addresses in. The WinMain function isn't part of an export table anywhere. It's deep within the code. So how do we call it? Well, we do know certain things. We know that we know the calling convention. We know its parameters, and actually we know its address in memory. This is the address it's going to be in memory, always. So we can do some sneaky things around that. In fact, we can write a function like that. Let me just copy paste all that in. So we can redefine WinMain in Rust as a function which casts a memory address that we know to be our memory address and call that. And Rust knows it's calling a std call, so it'll do the correct setup and expect the correct teardown on the other end of the compiled call. I did say it was going to be unsafe, but we can see that running as well. Let's try that. Finished. So you see it prints hello world down here at the bottom. Also the text initializing sound now. If I exit, goodbye world. So we've started so from the Rust end of things, by examining the decompiled code, we can start calling C++ from Rust arbitrarily. And that's pretty powerful. Of course, there's a lot of boilerplate here. So in my project, I changed this to this call engine call here. So basically, I did a little macro so that I just fill out all the boilerplate for us. So it almost becomes like an extern declaration. That makes sense. Hopefully that makes sense. So that's where we've got so far. It's far from safe, and to use the call of cowards everywhere, it works in my machine. Right? But we have, by a bit of knowledge of calling conventions, convinces that it should work as given. Raises a lot of security concerns. Yeah, it's interesting how these things tie together. Like, what makes Rust it's not Rust specific, no, but what makes Rust pretty good in this case for doing this kind of thing is that it basically contains every calling convention under the sun, including this call. You need to use the nightly pipeline to get this call in Rust, but it's hard to find a language which so happily caters to all the potential calling conventions that could be within a compiled binary and being able to address them. That's, I think, a really great feature of Rust for this purpose. Because you don't have classes in Rust. Why would you ever need a C++ specific calling convention for 32-bit systems? You don't get this in 64-bit anymore. But, right, so next steps is going to be calling Rust from C++ code. And this is mighty trickier, right? Because we have the compiled binary and we need to modify that. And this requires the introduction of a new technique called hot patching. The key to hot patching is we want to replace a C++ function in the binary with a Rust function. So we don't care about the contents of that function, don't care about its state. We can corrupt it as far as we need be. We just need it to start calling Rust code. I've got a diagram here to show for this. So the idea with hot patching is that you have a function that says foo here is a C++ function that's come from the original engine.executable. What we do is we modify the first line of the function to jump, set the instructions pointer to a relative offset somewhere else. And it carries on execution through our Rust function, which we bar here. Now, again, through calling conventions, provided bar and foo align up in terms of their calling conventions and parameters, then this jump, provided it doesn't modify the stack or the registers and only just modifies the instruction pointer, that should still again be valid for calling Rust code. And when the Rust code finishes and it comes to cleanup, it should return back to the original caller afterwards, because it is the pointer to the original caller that's on the stack to return to. So provided your jump does not modify anything, this is possible. So if you can imagine, if we wanted to modify some arbitrary function here, like get flight recorder. This is clearly flight recorder's a singleton somewhere, the looks of things, because it's returning a pointer to memory allocated in the .data layer. So this is and it's a cdeco call. So there's a lot of hints here that this is a call to some static singleton somewhere in the system. But if we wanted to change this to return our own custom value, then we would change this line to a jump to Rust code. The question is how to do it. By this point, don't want to actually modify the binary any further. We're done modifying the binary. What we do have, however, is the ability to say that, well, the text section is loaded into memory. We can just modify the program in memory. Executable instructions are just data. So we can just modify the data that we're running on. And this comes in 4 different steps. So let's just find the injection section. So unfortunately, yes, I am showing code here, the bane of everyone, because I know code's not always interesting to look at, but I'll go through what's going on. So first, there's a little Windows 32 program function called virtual protect, and it lets you change the protection mode of memory you're accessing. So here, we can just change the executable memory to write memory. We treat it like data, so we add a jump instruction, which is OXE9, and the relative offset we want to jump to, which is a Rust function somewhere else. You set the memory region back to executable code, and then all you have to do is flush the instruction cache after the fact, and so that everything agrees to your new set of changes that you've just made to your program while it's running. And what this looks like on kind of the grand scale, for example, I have this app and I just want to replace all these C++ functions that I know are at specific memory addresses, because it's always going to be at these memory addresses for an executable in memory. You can just start going ahead and replacing them with an equivalent that, provided it follows the calling conventions as demonstrated there. Terrifying. But in terms of what time is it now? It's 10 past, right? Okay. So only got a little time left, so I'll just take the chance to just talk about kind of the Norn Pulse project's got so far. So primarily wondering where it's going so far. You saw the hello world, goodbye world example. Well, here's kind of what that looks like in the current up to date. We're able to, the flight recorder is replaced with a custom Rust logger, and we actually have control of the main game loop. And what we're doing in the main game loop is we're calling SDL2, and we're trying to use SDL2 to control the key bindings and control the timing of the game. And the aim long-term is to replace the old DirectX rendering engine. God knows how old that one is with kind of an STL2 frame buffer. But that's still a work in progress. The rendering is actually really hard. So that's kind of really all I had time for. I do have a little more on marshalling structures, but depends if you're interested or not. I will give the floor back to the group for discussions or condemnation or any questions.
That was brilliant. I'm sure there's lots of questions. I can think of a few. Just check. So the aim here overall is that you want this to be playable forever. So you're trying to modernize the IO bits of the code. Is that kind of like, and the rendering, so that those bits that are more likely to break keep working?
Yeah, I think that's a fair summary. So, in my head, it was always a case of, well, you've got the original executable code. Yeah, original executable. If you could start replacing portions of that with unsafe Rust wholesale, you would probably eventually reach a point where you could start converting that unsafe Rust back into safe Rust. So you start refactoring the unsafe Rust back into the world of safe code once again. Unfortunately, where it is and where it may languish forever is in the kind of the unsafe Rust sphere, or the very, very unsafe Rust sphere, as this is. Oh, thank you. Thank you very much. And we've got any other questions?
I was just wondering, Neil, what your background was to have figured out or to have delved in enough to understand how everything works at low levels and start putting the pieces together with modern tools. Was it just a hobby, or is it?
It was just a hobby. I learned a lot through just doing this primarily. I work in forensics now, but I didn't work in forensics when I started this, so I can't say any one thing. But yeah, there's a lot of good information on the internet for this kind of thing. So I think it is accessible, like more than people realize. We just kind of, if you need to know what to look for.
Yeah, there's clearly a lot of details. You make it look simple when you've brought together the right details in the right order.
Well, thank you very much. Internal tools debugging shown here. That's a great question. A book and online resource.
Can you read that out loud, just so?
Oh yes, sorry. So the question was, can you recommend a book or online resource to learn the tools debugging shown here? I think a great starting point is actually just looking at the Ghidra documentation, because this has I've only kind of really touched on kind of a level of the functionality shown here, but this has very comprehensive contents here. This has a lot of documentation online for how to start decompiling, how to make sense of what you're seeing as well. Likewise, the unsafe Rust book is actually really good for all of this, especially in terms of how to actually call beyond the Rust layer. That's actually helped me immeasurably, especially its section on types and stuff like that. In terms of the forensic side of things, I don't have anything on the top of my head, but if I can think of anything, I will post it in the chat or on the Discord afterwards.
Is there a book for unsafe Rust, or do you mean the Rustonomicon?
Yes, that's the Rustonomicon. Thank you.
Rustonomicon. Okay, cool. Sorry, thank you.
I noticed over the last year or so, there's been a number of products that have all started offering sort of hot reloading of DLLs and modules without you having to rebuild or relink the system.
Mm-hmm.
Those sort of, or do you imagine that those are industrial scale versions of pretty much the same techniques. So Visual Studio has started adding the ability to hot swap functionality. And I know, remember the guy's name, Lower is very keen on his game development, and he's very keen on a very short iteration cycle, so wants to cut out compilation and linking wherever possible, while keeping running with changed codes. I just wonder if you reckon they use similar techniques for the actual linkage points and pointing, or getting the control cursor, the program cursor, to actually just resetting that to their new module.
That's a fascinating question. So as I mean, I reckon I know about hot reloading in terms of like managed languages like C# and the like, but I'm not too familiar with it with the likes of C++ or Rust. And is that what you're saying is kind of available now? And
from the last Microsoft, when they did their virtual conference earlier this year, or maybe it was last year, I can't remember which one, they were pushing it as one of the areas of functionality they now had available. Pretty sure it was for C++, not just the managed languages.
That's really fascinating. I hadn't heard of that before, but I have to look into that. In terms of your question of, I think it'd be pretty reasonable to say that could be the case, because you could just change the address in the addresses in the IAT, and then they would just start calling different things under the hood. So that would be my guess, but there's probably a whole lot of like complexity under the hood, right?
Yeah. Thank you, Kira.
Oh, thank you. Rust Talks Nomicon. I had no idea that's so sorry, so I'm just supposed to tell you can type rustup docs -- nomicon to see a local copy of the Unsafe Rust book. I had no idea that. That's very cool. Rust has everything. Oh. Right.
What would you say was like the hardest bit of where you're at so far? Like, what was the bit that like surprised you? Was there anything that took you far longer than you expected it to?
There was definitely a couple of stumbling blocks. I mean, by far the most difficult I remember at the time was just being able to find the right set of instructions to call a different function in editing the binary. The hot patching, I remember actually working relatively flawlessly. What became a bit more difficult, as I recall, was marshalling structs about. That was a bit awkward. If people, stop me if you already know all this before. But I do have something here for. Let's see if I can find the right one. Yeah, there we go. So I'm not a struct or a C++ struct man at the best of times. If you try to say the struct here, say, well, what's the size of the struct in memory? Yeah, the answer is, well, depends on your target architecture, but you'd certainly say it has to be no less than 6 bytes. You got a 1 byte, 4 byte, 1 byte size there. But there are actually alignment constraints in C and Rust, both, which say that, for example, I32 can only be placed on the stack and addressed as a multiple of its alignment, which is its size, which is 4. So you can only place this struct on places that are multiples of 4, which means if you have an array of these structs, it means that they their fields have to be on alignment of 4. So the size of the struct is actually 8. Another weird thing is that the fields that you have in Rust is that they It doesn't matter what order you have them in Rust. The Rust will happily reorder them to find the smallest possible size. You have actually no ordering guarantees. So this is also 8. And if I actually just read the Rustomicon properly, I would have figured this out immediately. But there is a C representation that exists, and it pretty much follows the same system as Rust in terms of alignment and size. So this here is 8 as well. But if you order them like that, the size suddenly becomes 12 because it's a 4-byte alignment, 4-byte alignment, and an additional 4-byte alignment. And there was a lot of structs as I was building them up, even when I figured this out, that were causing all sorts of subtle bugs because I had miscounted the alignment, carefully adding the data in as it goes on. So like in Ghidra, where is app class? So we're in engine, should it be here? App, edit data type. Oh, this is the wrong one. It needs to be the original. Sorry. So this data type here, I've partially filled it in, but there's still missing sections to it. So as you're kind of going through a struct and trying to figure out what's in it and what's not in it, you can easily not realize what the true alignment of the struct is until you have a complete picture of what's going on, if that makes sense. As you, because the alignment of your struct is itself based on the alignment of the underlying types. So what I ended up just doing was just making everything C packed, which forces everything to be alignment 1 at all times. The only consequence to this is you have to manually put in your padding, and that you can't references to fields in Rust. Rust doesn't let you take references to any of these fields anymore. Rust demands you have to take actual alignment. Rust demands that they have to be aligned properly for you to reference the fields full stop. So you start having to like do use a little memory of field macros in Rust to actually access the fields of this struct from then on. So that's a bit of a long-winded thing, but I found that quite hard to deal with.
I think you were just showing in Ghidra with all the types. What is this? Sorry, so this is your structure. Yeah,
so this is the struct in, or how me and Gitra have decided that the struct should be in memory. So I can set the size of the struct in Gitra. I can fill in the fields and what their types are, and what Gitra returns for me for my efforts is let's look at this constructor for app here. The constructor, C++ secretly under the hood, it will so this call, it'll pass into this item, and in the constructor it will start setting it up. But this is quite this is the wrong one. So here it's pretty ugly what's going on. But once you start putting the struct contents in, Ghidra starts giving you better quality data in terms of what's actually going on. So it's in your best interest to actually try to inform it what the struct fields are, what their types are, and you get kind of better output. So it's kind of a big discovery process as you try to wrangle out the truth from it. Does that make sense?
Yeah, so there's just one massive struct, and this is all the fields in it. How did you find out what they were? How did you figure out what they were?
A lot of trial and error for that one. Like I showed in PE Bear, for whatever reason, I think because the original creators marked some fields decal export, that it does have some class names and class functions within the export table, which Ghidra could reapply, which gives better additional context. And an interesting fact about Linux, is that on Linux, the actual when you compile a C+ binary on Linux, everything is put into the export table by default, and you need to strip it after the fact to actually clear out all the extraneous information, which you want to do if your code is proprietary. But if you have the LE file, you can load that into Ghidra, and it will have more information than you'd expect than in the Windows side of things, because the person whoever made that back in the day didn't perform stripping, so it actually has a lot more context than the Linux stuff you can apply for the Windows stuff.
I can remember a simple version of that, much simpler than what you've been doing. But back in the 80s, it used to be fun just to do lots of peeking at the memory once you'd loaded a game into memory, find recognizable strings from the game, and then just poke your own equivalent length strings on top of them, so that when you run the game, it's up your name instead of Captain Picard or whatever. Wasn't very sophisticated, but it showed exactly what would happen if they've got unobscured text in there. You could easily change it to anything else, and I guess it's just a more advanced step to start replacing the actual jump pointers or any of the other behavior or the data. That was the simplest version I could remember of looking for plain text.
Oh, that's quite cool. Yeah, I remember doing that kind of thing back in the day.
So we're rapidly approaching time. I have one more question. If one of us wanted to run the executable with your Rust code in it, so presumably they have to copy down your DLL and the executable. And have you modified the executable itself?
Yeah, so in the GitHub repo, if you wanted to play with it, I said if you wanted to play with it, the Gitra root did provide the modified executable and the Rust code for building. What I don't supply, obviously, is the actual game content itself. I'd very clearly say, this is a modding thing. So buy the game or get your old copy off the shelf, install that, and you can replace the exe and build the DLL and so on. So all in the spirit of good
all
modding.
Above board, yeah.
All above board, yeah.
Awesome. Any more questions in the final minute? Oh, just big thank you, Neil. That was great. I think you see from the chat that everyone loved it.
Oh, thank you. Thank you very much, all. I appreciate it. I was definitely nervous. I wasn't sure how people would go down, but I appreciate it a lot. Thank you.